I think you can go ahead. The recording can start. The recording has started.
Okay. Hello. I would like to thank the organizers for the opportunity to talk today. And my lecture is going to consist of two parts. So in the first part, I would like to recall what happened earlier and elaborate on the different notions introduced, and we portray the general picture and tell you how the situation mixed characteristic differs from that in characteristic 0 and positive characteristic. And in the second shorter part of my talk, I will go over various applications, culminating with the minimal model program for threefolds, whose residue characteristics are larger than 5. So let me start with recalling the vanishing theorems. I'm going to state a variant thereof, as stated in Yoshikawa Takamatsu paper, as Shaw explained last time. And this follows from the result of bar graph and maybe a slightly more general form thereof from the 7 authors paper, and Kodaira vanishing in characteristic 0, which in this generality is known due to the recent work of Takumi Murayama. So R is an excellent domain, and X over I is a proper regular scheme. I mean, you can also assume is KLT plus Cohen-Macaulay. Let me just focus on the regular case. I'm going to pick a line bundle, which is ample, or maybe more generally, semi-ample and big. Then what happens is that there exists a finite cover such that, oops, sorry, hi of y omega y tensor, oops, I make the same mistake, let's call it M. Tensor the pullback of M mapping to hi x omega x tensor M. This map is a 0 map. So the proof goes as follows. First, you localize the characteristic 0. You use Kodaira vanishing characteristic 0 to see that the cohomology classes are p-torsion, and then Bargraph's result tells us that there exists a finite cover that kills p-torsion classes, or dually that the trace map is 0 on p-torsion classes. However, I would like to emphasize that somehow this is not the result we use in our 7 authors paper. In a way, it's very important in mixed characteristic to go all the way to x plus and somehow use vanishing theorems on x plus itself. And I'm going to elaborate on this phenomenon many times throughout this talk. So now let's move to the next page. Let me also copy the Jamboard. So if you want to move between pages, it's all in the chat. Okay. So I'd like to elaborate on this notion of the T regularity that Shaw talked about here. I'm going to talk in this variant, which is called plus regularity. So throughout my talk, I will assume that R with the maximal ideal M is a local domain which is complete. And it is essential that the base is complete. Many of the results I'm going to talk about are either unknown or possibly even false if we do not assume completeness. I'm also going to assume that the residue field is of positive characteristic. We're mostly going to be interested in the rings of mixed characteristic, so that, for example, R is ZP. Now, X over R is going to be a normal integral proper scheme. If you are interested in the local situation only, you can assume that X equals to spec of R. And last, I'm going to pick a line bundle L, and it corresponds to the divisor, which I'm also going to call L. And I'm also going to assume that X is either Q factorial, or more generally, that M, which is equal to L minus KX, is Q Cartier. Okay, now I'm going to define this set of sections B0, which should behave as if Kodaira vanishing was true for them. So I'm going to take an intersection over all finite covers of the image of H0, Y, O of Y, KY plus the pullback of L minus KX inside H0XL. But what really happens here is that Well, L minus Kx, that's M. So this is like Ky plus pullback of M. And L corresponds to Kx plus M. So that is the usual trace map tensored by the pullback of M and possibly reflexified if needed. Okay, I can also define the variant thereof for all alterations. And again, the study of how these notions differs for finite maps and alteration is very important. And I'm going to elaborate on that in a second. So I have O of y, ky. But now, since I'm pulling back a Q-Cartier divisor, it's not necessarily integral anymore. So I need to take the round up. And mapping it inside OX L. Now, for the sake of future references and proofs, I'm also going to define a birational variant of this notion. So I'm taking Fy to X to be projective birational maps. And I'm taking exactly the same definition as in the line above. So let me just not write it down. And now, if X equals to spec of R, then B0 bir XOX, by definition, is exactly the multiplier ideal sheaf of X. So this is the multiplier ideal sheaf. Sorry, this may be not readable. Right, it's like I'm taking a roundup of appropriate relative canonical device. And if you look at it more carefully, maybe we also assuming implicitly resolutions, because otherwise the multiplier ideal sheaf is a little bit tricky without resolutions. But let's me just not delve into this technicality. This B0 bir is nothing else but H0 of X, L tensor the multiplier ideal sheaf of X. So like if you look at this condition, I'm looking at some subset of sections if I look at it for birational maps, a subset of sections of L which admits this additional vanishing conditions. So they need to vanish on this multiplier ideal sheaf. Okay. So now let me take, so in a way, this definition of B0 is very hard to work on because it's an infinite intersection. And moreover, if we pick a section in B0, it's an image under the trace maps of some element on finite covers. But we do not insist that these sections are in a way related. So in fact, what we show is that this B0 is equal to, which we can swap the image with the intersection. So what we get is that is the image of the limit under all f finite of this H0y, OY, ky plus the pullback of M. And this limit, just right, we look at the image of this limit inside H0XL. So in other words, right now what happens is that we can, on every finite cover, we can compatibly pick sections, which are going to map to our element in B0, in a way that if we take a bigger finite cover, then the section chosen there is going to map to the section chosen on the smaller finite cover. And we have the same result for the alteration one. And that somehow now we have this collection of compatible sections for all finite covers. In a way, we can go even a step further. As I said before, it's still hard to work with limits. So we really want to have like an intrinsic object we're going to work with. And that's going to be defined via Matley's duality as appropriate local cohomology of X plus. So this, in fact, is also equal to the image of HDM, where D is the dimension of the of X, OX, KX minus L into HDM X plus OX plus of the pullback of kx minus L. Remember that kx minus L, that's exactly minus m. Okay, and I'm a little bit sloppy here because this m lies on the base ring, but I'm looking at my x. So what I really mean here, I'm taking the derived push forward of this onto R, and on this R, I'm taking the appropriate maximal local cohomology. But now the upshot of this is that this can be, sorry, and now I take the Matley's duality here. But now the upshot is that this object can be intrinsically defined on x plus itself. And that's what is really kind of useful for many of the proofs. Okay. Let me move on the next slide. So, and the second result is the comparison between the finite and the non-finite part. So let me state the following result. This is just, I'm going to be a bit vague, so it's not maybe precisely true on the nose, but at least philosophically it should be. So that's what Barga told us, that cohomologically, whether we look at alterations or finite maps, this should not matter. So what happens is that if we take the limit over all f y to x finite for Rf star O of y, and maybe we are going to take a p completion thereof, and the limit is taken in appropriate sense, so I didn't want to get into details, and f y x, which is alteration, Rf star. I mean, I should also recall that, yeah. So I mean, for alteration is going to be the projective generically finite maps. In other words, the compositions of finite maps and projective birational maps. Okay. But what one can use this for is that you have the following theorem. Seven authors paper. Is that B0 XL is equal to B0 alt XL. So let me remind you that this B0 is defined with respect to finite maps, and B0 alt is defined with respect to all alterations. So maybe this is not surprising that this kind of one should imply another, because you see what you can do. You could take the say dual, and then you get all the trace maps, and you see that kind of looking at trace maps and looking at alterations, the same thing. Of course, in practice, this is much more work to maybe make the deduction. I think that it maybe justifies why such a statement should be true. Okay, so having defined B0, now I'm going to move to a particular type of varieties for which this B0 is nice. And these are going to be globally plus regular varieties. So I'm going to say that X is globally plus regular, X as before, if O of X, the push forward of O of Y, splits for all f y to x finite. So in other words, if X is a splinter and is locally plus regular, so is a property of singularities, if all local rings are plus regular. Okay. So let us make a few remarks about this notion. So let us start by comparing how it looks, and basics of it in zero, positive, and mixed characteristic. So if X is normal over a field of characteristic 0, then all finite maps split automatically. It's very easy to see using like trace map, or in other words, the averaging operators, which is another justification why this might not be true in other settings, because since if the trace map is multiplication by p, that's invertible in characteristic 0, but it's 0 in positive characteristic, and it's definitely not invertible if you work over ZP, for example, in mixed characteristic. But in characteristic 0, for all f finite, the map splits. So this notion is kind of meaningless. Now, in positive characteristic, we have a very particular and nice finite cover. That's the Frobenius. And now the splitting.
So excuse me.
Yeah.
So Jakub, I think there was a question in chat whether by finite you mean finite surjective, right?
Yes, I always, yes, sorry, yes, finite surjective. Mm-hmm.
Thanks.
The splitting of Frobenius in positive characteristic is a very important notion, both in positive characteristic commutative algebra and algebraic geometry, and that is called, and if it's called F splitting. So if it splits, it's a very kind of a non-trivial condition. And now in mixed characteristic, this notion is very hard kind of to study. So even the fact that if X is regular, then it has locally plus regular singularities. That's a very non-trivial fact, which in fact is equivalent to direct summit conjecture. Like even if, in fact, is exactly the statement of direct summit conjecture that regular links split under finite maps. So even verifying that like AN or PN are plus regular, that's really kind of a deep result in mathematics. Okay, so that's about kind of the very basics of this notion. And now let's maybe let me give you a criterion for plus regularity in terms of this B0 I just defined. So what one can show is that X is globally plus regular if and only if, and that's not too hard to see after what I told you, that B0 XOX equals to H0 XOX. So in other words, that all so for all F finite, H0Y just 1 second. KY minus the pullback of KX is surjective onto H0 of X OX. So for all finite maps, this kind of a relative trace map is surjective. Now, if I said split surjective, then it will be almost obvious that these conditions are equivalent, because what you do, you know that trace map are split surjective. If you dualize them, you also get that this pullback, which is the dual, is also split, and which is the global plus regularity. And the fact that kind of a surjectivity implies split surjectivity is a common trick in this theory. Let me not delve into that. But also, I just told you that B0 is equal to B0 alt. So this is equivalent to saying that that B0 alt XOX is equal to H0 XOX. So in other words, all the trace maps for alterations are surjective, and that's exactly the notion of global global T regularity that Shaw talked last time. So these two conditions are in fact equivalent. Okay, so this is the criterion. Now let me explain that this plus regularity is a two-handed beast. It comes with the geometric datum and with the arithmetic datum. So let's see what's the geometric abstraction for being plus regular. So locally plus regular. Maybe let me assume also Q Gorenstein to just make sense of this. Implies KLT. And now the proof is very simple. Let's say that X is equal to spec of R. Then by definition, or by what I told you in this criterion, R is equal to B0 XOX, which is equal to B0 alt XOX, which in turn is contained in B0 bir XOX, because we are taking the intersection of a smaller collection of alterations, the projective birational maps. But in the local setting, that's exactly the multiplier ideal sheaf of R. So the multiplier ideal sheaf is trivial, which implies that we are KLT. As in the global setting, this is not known as a conjecture. It was stated before by Shaw, and this is like really hard, even in positive. It's completely open and super hard in positive characteristic as well, is that global plus regularity implies that we are log phenotype, so that there exists a Q divisor delta effective one, such that x delta is KLT and minus kx plus delta is ample. So it's really kind of on the final side of the story that you can't expect an arbitrary variety to have this globally plus regular property. On the positive side, if you are globally plus regular, you have a lot of very good properties. And one of them is Kodaira vanishing. So let me assume that my x is regular and globally plus regular. And this can be weakened. There are variants of this statement in the 7 authors paper and the Takamatsu Yoshikawa paper. And I claim that Kodaira vanishing holds. So that hi x omega x tensor A is equal to 0 for I greater than 0 and A ample. Okay, now the proof goes as follows. So by the result I stated in the beginning, you have a finite cover such that hix oops, I'm just going to the next line. There's an y omega y tensor the pullback of A map to 0 map to x is a zero map. On the other hand, by taking duality, this plus regularity gives us a splitting. There exists a splitting by plus regularity. But the summand cannot be like have a projection onto a summand, can't be a zero map. In other words, going left and right must be an identity, but it factors through 0. So the right hand side is 0 as well. Okay. For many of the results I'm going to state now, I'm going to make an additional assumption star that if I'm given a variety and an x and divisor s, I'm going to assume that the codimension of the singular locus of x union with the singular locus of s is at least 3. The reason is that I don't want to deal with so-called the different, but if you're okay with that, you can just adjust all the statement by the different, and they will be all correct with such an adjustment. Okay, so we have the following theorem of the 7 authors paper. So now I'm gonna assume that kx plus s is Q Cartier for S normal integral divisor. Again, both of these notions can be weakened. Let me not delve into it. Then, so last time Shaw explained to you that if we have a section in B0 on a divisor, we can lift it to a section of H0, just a normal section on X. So that what I'm going to tell you is like kind of like an explicit, it makes that explicit. So we have that B0S XL mapped to B0S restricted to LS is surjective. And I have not defined the left-hand side. I'm going to define it in a second. But just let me point out that the left-hand side is a subset of sections of L, and the right-hand side is a subset of sections of L restricted to S. So in other words, the sections on S which are in B0, they can be lifted to this explicit thing, which is B0S. And this theorem is very much unknown if the base is not complete. It's really essential. It's one of the most essential parts when the completeness is kind of necessary, and we do not know whether it's true or not without that assumption. Okay, so let me define this B0S, and that should be thought of as a an adjunct version of B0. So B0SXL is equal to the intersection over all F y to x finite. Now, I'm going to also pick sy, which is going to be an irreducible component of the pullback of S. So a pullback of S under a finite map might split, and I'm picking an irreducible component. And I'm going to do it in a compatible way, so that they are compatibly chosen for different finite covers. I can always do that, but let me not delve into the details. Maybe I should also say, which I have not done yet, that when I pick finite covers, I always pick them in a fixed algebraic closure of the finite of the fraction field of X. Okay, so now I'm taking the image. So it's completely analogous to the previous definition of H0. I'm taking the image of H0 of y, O of y, ky plus sy plus the pullback of L minus kx minus s, and mapping it into H0xl. So you see that I added this minus s here and plus sy here. And it's easy to see that this is contained in B0xl. Indeed, this sy minus the pullback of s is a negative divisor. So this gives me more conditions on more restrictions on the left-hand side, that the left-hand side must vanish to a higher degree. So the upshot is that now we can rephrase it by saying that the sections on S can be lifted to the sections in B0. Can be lifted to sections in B0. So sections on S can be lifted to sections in B0xl. But I need to introduce this intermediate notion to kind of make sense of that statement. Okay, let me make a remark. That if X is equal to spec of R, then B0 of S beer XOX. So I can define the same thing, taking the intersection over now birational maps as before. And this thing is equal to exactly the adjoint ideal of R. So that it is not, so this is this ideal that restricted to the boundary recovers the multiplier ideal sheaf. So it's not true in general that the multiplier ideal sheaf restricts to the multiplier ideal sheaf on the boundary. It is true for this adjoint variant. And so you should think of this B0S as being kind of like an adjoint version of, like the global version of that and mischaracteristic version. Like you can't lift multiplier ideal sheaf to a multiplier ideal sheaf, but you're going to lift it to this kind of an adjointy version. And in general, this B0, maybe in general, this B0 as beer XL is equal to H0 XL tensor with this I as of X, which is pretty funny because that's exactly kind of in modern birational geometry. That's exactly the set of sections you would use for proving theorems. Like this is an important component, say in Haeckel-McKernan extension theorem. So this B0 again kind of interpolates between these different notions that are useful in characteristic 0 and in positive characteristic. Okay, now let's get a little bit technical. So let it make it even more technical. So I'm going to introduce one more notion, which is an analog of this global plus regularity in the adjoint version. So you should think of this as KLT corresponds to PLT, that this new analog is going to be kind of work in the same way. So I'm going to say that XS is purely, so like think about P in PLT, like purely log terminal. And this corresponds to purely along S, globally plus regular, if and only if, that's my definition, B0 S XOX is equal to H0 XOX. And I could also define it in terms of certain splittings of certain trace maps, but let me not do that here. And the reason I introduced this, so let me also point out that XS is purely globally plus regular. And this implies, because B0 of S is contained in B0, that X is globally plus regular. So right, if B0 of S is everything, then the B0 is also going to be everything. Okay, so I did introduce this notation to make the following statement, which follows from the previous lifting result, but maybe you don't need the full power of that here. So this is what also Schwede talked about last time. So if I'm going to assume that minus kx plus s is ample, or maybe more generally big and semi-ample, let me also denote by pi the map from x to spec of r to the base. Then xs is purely globally plus regular, maybe over the neighborhood of pi of s, if and only if, oops. Can you see my screen? Sorry, I just touched something. Right, can you see?
Yep.
Can you see me?
Yep.
Yeah.
Yep.
Okay. Perfect. If and only if. If and only if S is globally plus regular. In particular, if S is globally plus regular, then XS is purely globally plus regular. But pure globally plus regularity implies globally plus regularity. So in other words, if a reasonably chosen hypersurface, or is a reasonable hypersurface, is globally plus regular, and the ambient space also going to be plus regular. So that's one of the key tools for showing this plus regularity, because we kind of can decrease the dimension by showing that something is plus regular. And this notion of pure plus regularity kind of makes this maybe if and only, makes this statement if and only if. So now I'd like to talk about key differences between plus regularity in positive and mixed characteristic. So in positive characteristic, this B0XL can be calculated on a single finite cover. So for some finite, some fixed for some finite f y x. So all these issues I talked about, like taking infinite intersections, they're non-existent. Like in the end, this is like a very concrete object that just comes from a single finite cover. But the mixed characteristic, that's not the case anymore. So let me give you an example, which is like fairly simple. So we're going to take a smooth elliptic curve over ZP. And then I claim the following. Oh, sorry. Then B0 EOE is equal to 0, but the trace map is non-zero for all finite f. So you are gonna, B0 is gonna be killed, but not by a single cover. You really need all the covers to see that. Okay, so the proof of 2 is very simple. So the trace of f, if you invert P, we are in characteristic 0 now. In characteristic 0, everything splits. So there's nothing about elliptic curves here. This splits, so non-zero. So we really need to see the point, C1. Okay. So 1. So we need to poke our E with some finite covers. In positive characteristics, we would have the Frobenius. But since we are in an elliptic curve, there's another nice map, which is the multiplication by P to the n. And it's not hard to see that on H0, this map is also just a map that multiplies by P to the n. And so B0 EOE is contained in the intersection of the images of this trace map, that's equal exactly to the intersection of P to the n ZP, which is 0. However, this example is in a way a little bit disappointing because the reason why we get this is purely geometric. There's no arithmetic condition here. We do not assume that the P fiber is a super singular elliptic curve. What really happens is that if you took the cone, that you'll be able to see that this B0 here is 0 by blowing up the origin and using the fact that the singularity is not KLT, but just log canonical, which in a way corresponds to E not being log Fano. So it's really kind of a geometric reason that this fails. So it'll be kind of interesting if there is an arithmetic reason as well. Or maybe to put it in other words, sorry, let me define the mixed characteristic multiplier test ideal. So a mixed characteristic analog of the multiplier ideal sheaf as B0 of spec of R, O spec of R. And there are two big open problems, which are probably the most important at this point in the theory. So the first one, is it true that tau plus of R can be calculated on a single alteration? As I said, in the projective case, the global case, that's not true. Neither for finite covers, nor for alterations. But we do not know what should happen in the local setting. So it is not clear whether this tau plus R can be calculated or not by on a single alteration. And if that would be true, this would imply the following. It would imply that tau plus of RF is the same as tau plus of R localized at F for some element F in R. In other words, that tau plus localized. However, the second property could be true independently of the first, even if the first one is false. And that's really kind of slows down the whole development of the field, because this is such a natural property that the fact that we don't have it is really kind of causes a lot of trouble. I mean, there are special cases. So we have special cases in the case of somehow. Oh, I'm not getting the details, but there are special cases in the 5 authors paper, and there's also kind of can also get some other special case in a different direction. I mean, using all this machinery of perverse sheaves and the Piaget-Riemann correspondence, as mentioned by Bhatt in the second talk. So these are really kind of the two main open problems in the field right now, I think. Okay, so now I would like to kind of wrap up what happened and compare different settings. So I'm going to draw a huge table. So first, in characteristic 0, we have that B0 alt XL is equal to B0 bir XL. The reason is that every alteration splits into a finite map and a birational map, and finite map splits. So having images under trace maps under alterations is the same as looking at images under birational maps. In mixed characteristic and positive characteristic, that's definitely not true, but we have a way to compare finite maps and alterations. So B0 XL is the same as B0 alt XL. And the same in positive characteristic, but let me maybe emphasize that kind of in mixed characteristic, that's maybe a little bit more meaningful in a way that it gives another reason why this mixed characteristic setting really bridges the gap between characteristic 0 and positive characteristic. Now, in positive and mixed characteristic, this notion depends on global geometry. However, in characteristic 0, it does not. It only depends on the multiplier ideal sheaf. So it only depends on the singularities. On the other hand, in positive characteristic, you can calculate this on a single finite cover. And in characteristic 0, we can calculate this on a single resolution. Log resolution. That's not the case anymore in mixed characteristics. So it really needs all finite covers / alterations.
Sorry, Jakub, can I ask something? I'm not sure that I understand. So in characteristic 0, right? So this is global sections of L twisted by the multiplier ideal, right?
Mm-hmm.
So how, I mean, how can it depend just on the singularities? It's still a global.
Sorry, what I mean is that as a subset, right. Yeah, okay, I'm a little bit vague here. I mean, also they're going to depend on this line, on the line bundle somehow itself. But it's not, we can't express it as some kind of a sections with an additional vanishing condition, because it won't also, right? That's what I'm trying to portray. So in the right-hand side, you really see that these are these sections that vanish along some locus. Mm-hmm. So on the left-hand side, it's not. It's really kind of the, there's no way of making such a statement. Mm-hmm. Yeah, thanks. Okay. And last, this B0, oops. This B0, if we look at these varieties, for which this B0 is nice, so this detects global plus regularity in positive characteristic. And maybe for experts, we mentioned that conjecturally, this is equivalent, should be equivalent to global F regularity. But we do not know. It's a very hard conjecture, even in positive characteristic. We only know that global plus regularity implies, F regularity implies global plus regularity. Now in mixed characteristic, that's just detects global plus regularity. And in characteristic 0, this detects chaoticness. As we proved earlier. So let me make a few remarks. So first, somehow we see that the study says singularities in characteristic 0. We are going to poke our variety with projective birational maps. In positive characteristic, there's a way to do that by poking our variety with the Frobenius. In mixed characteristic, what happens is that we do not have the Frobenius, but somehow what Varga's result says in a way that every Frobenius can be approximated by finite covers. On the other hand, the fact that B0 is equal to B0 old points out that somehow the information that we recover from birational maps can be read off at the characteristic P fiber through finite maps. In other words, if you look at your characteristic 0 variety and you take a finite cover and you extend it to the model, then the way this finite cover acts on the special characteristic P fiber is going to tell us something about the characteristic 0 geometry of your variety. There's some kind of like an interesting way that these words combine together. And last, let me mention that in a way, this B0 old, sorry, this is what sorry, I should write of course, H0 XOX, sorry. And last, let me mention that requiring that B0 old equals to H0, it's not really meaningful, at least geometrically it's not meaningful in characteristic 0. That's only like condition on singularities. So as a kind of a global property is kind of meaningful. On the other hand, it kind of points at something very interesting. So in characteristic 0, to have vanishing theorems, that's only a condition on singularities. If you have Kelty singularities, you have Kalamata-Vivek, Kodaira vanishing theorems. That's very false in mixed and positive characteristic, even for regular schemes. However, what happens is that if you are log Fano or Fano, then you often come with vanishing theorems. So in the setting when you work with Fano varieties, you often have vanishing theorems to your disposal, and that somehow justifies why this notion B0 equals to H0, which in particular, at least conjecturally, should imply that we are log Fano. It's kind of very useful when you have a lot of in this setting. So when you have a lot of Fanos, this notion kind of becomes very, very handy because we often have vanishing theorems to our disposal. And the minimal, and that's why this is so useful in the minimal model program, because the minimal model program is in a way a surgery on sub-Fano varieties. We remove some Fanos, we put them back like in flips, or maybe have Fano fibrations. So you see that we are dealing with Fano varieties. These kind of notions come very handy, but maybe it's not clear that this will be useful if you study like non-Fano subvarieties and some varieties of general type. Okay. So that's about it for the first part of my talk. So now I'd like to move to applications. So first, let me mention what Schwede talked last time, which is the three-dimensional semi-stable minimal model program, and this can be used in the study of semi-stable models. In particular, that's kind of very useful for the study of the arithmetic properties of varieties. The second application I like to mention, which is chronologically much older, is that of Linchuan Man and Carl Schwede. So I should mention that the local theory of what we are talking now was developed earlier by Carl and Linchuan, and they proved some beautiful results that led to many applications in algebraic geometry and commutative algebra. In particular, they proved the following results, which in this case was stated in a slightly different setting. So since we did not know that R plus is plus regular at that time, and also because the kind of their setting has a lot of many other applications, they work with these BCM regular singularities. However, they prove, just using the fact that R plus has this nice property after bar graph, they prove like immediately kind of generalized to this setting. So the statement is as follows: if X over ZP is proper and flat, and the base can be made much more general, but for simplicity, I'm going to assume is ZP, and KX is Q Cartier, then XP is locally plus regular. If this is true, then this implies that the characteristic zero fiber is KLT. And this is really fun because let me point out that there is an easy sufficient criterion for verifying plus regularity in positive characteristic. So for expert, what we do, we may apply Feder's criterion for checking F regularity, and then use the fact that F regularity implies plus regularity. And conjecturally, this is if and only if, but we only need the simpler statement. So in other words, say you are a complex algebraic geometer and you're given some polynomials and you like to check if the singularity described by them is KLT. Like okay, so you expect it is KLT, but you really need a formal proof. So it's really hard to do in practice. Then you can calculate the resolution, but that's super hard for you and for the computer as well. So what you can do, you can pick some random p, reduce modulo p, and then use this criterion. Which is very simple. You can just plug it into the computer, and the computer is going to calculate it for you. And this way, it's going to just tell you if you are plus regular. And if you are plus regular, and if you picked p like random enough, that's going to be the case, then you immediately get a formal proof that your singularity is KLT in characteristic zero. So this could be useful for verifying that a lot of singularities that were not known before are KLT. Of course, on the other hand, this doesn't help if you are going to show that something is not KLT because you don't know which prime to pick. Okay, so with what we...
Can I ask something?
Yeah. Mm-hmm.
So this is a statement about singularity. So why do you have to assume that X is proper?
Yeah, I'm going to explain this in a second. We'll see the proof. Mm-hmm. So let me just give a quick proof using what we showed already. So the special fiber is locally F plus regular. Then by inversion of adjunction, this implies that XXP is purely locally plus regular along XP. Then we show that this in fact implies that X is purely locally plus regular. Sorry, just globally plus regular. Sorry, it's just locally plus regular along. Along XP. And now this implies that X is KLT along XP. So the characteristic P fiber. And now this is where we use properness. So X is proper to deduce that X QP is KLT. So apparently it would happen that you are KLT along the special fiber, but you are not KLT in characteristic zero. And so now using properness, you can then see that that's in fact is not is not the case, because kind of the non-KLT locus would intersect the special fiber by properness, because it's going to be closed. That's
but I mean, you could expect that, right? I mean, it should hold without properness, but just as a statement in the neighborhood of the fiber.
Right, exactly. That's true in the neighborhood of the fiber, but it's not necessarily true on the characteristic zero fiber.
Maybe I can just say, Mircea, if you just pick a point on your fiber, you can verify it in the neighborhood of that point. And that's, you know, if you're just trying to show a particular point is KLT or something, then this is all fine. You don't need to do a soon proper.
Thanks.
So now let me move to the third application, which is in the 5 authors paper with Lin Chuan, Carl, Kevin, Joe, and myself. Maybe this is a little bit technical, but what is interesting is that it's purely geometric. There's no plus regularity coming in. So I'm going to take a PLT pair XS, which is 3-dimensional.
So sorry, before we move on, is it worth mentioning the Sato Takagi result too?
Yes, sorry, yes. There is a like a generalization of that to log canonical singularities by Sato Takagi. Thanks a lot. Sorry, kind of a much stronger statement. Okay, so if you have a PLT pair, then in fact this S is normal. So that's always true for PLT pairs in characteristic 0, but that's false in positive characteristic in general. However, both in positive and mixed characteristic, if in the low dimensional case, if the residue characteristic is greater than 5, that is in fact true. Maybe what is interesting about it, that was one of the starting points for the MMP for threefolds in positive characteristic by Haken and Shu. So somehow when we had it, we see that maybe we're on the path to in the end get this MMP. And then maybe an important component apart from the inversion of a junction that one uses to disprove is the following generalization of the result of Hara in positive characteristics. So if Rm is a 2-dimensional complete local domain and the residue characteristic is greater than 5, then spec of R is KLT if and only if is plus regular. So we know that plus regularity implies KLT, but in fact, if characteristic is greater than 5, we have the implication in the other direction. And this is exactly the 5 that's coming up in the MMP. This is the reason why there's this restriction on the characteristic. So last result I'd like to mention maybe very quickly is the special case of Fujita's conjecture, following the proof by Karen Smith in positive characteristic, now generalized to mixed characteristic. So this is from the 7 authors paper. Have X regular, flat, and projective over R. I'm picking D to be the dimension of X and T to be the dimension of R. I'm going to assume that L is ample line bundle. And because that's only a special case, I need an additional assumption. So I'm going to assume that it is base point free itself. Then the statement of Fujita's conjecture holds. So omega X tensor L to the power D minus T plus 1 is base point free. And I would like to point out that naturally you would like to assume that maybe X is locally plus regular. That will be a natural statement, but we do not know whether this holds in this setting. And the reason is that we do not have this localization property. So that's one of the cases when the lack of localization for the plus test ideal and some kind of a global variance thereof, kind of impedes our development of global statement. So we have a certain variant for kind of a summoned singularities in regular links, but not for locally plus regular singularities in general at this point. Okay, so now I'd like to move to the minimal model program. So you have the following result of the 7 authors paper. Now I'm forgetting that R was complete, so I'm gonna state it in full generality. I'm gonna take T to be a quasi-projective scheme over a nice ring. I'm gonna assume is excellent finite dimensional domain which admits a dualizing complex. And any ring you can imagine will have this, most of the rings you'll imagine will have this property. So, but you can take ZP if you want. I'm also going to assume that T has no residue characteristics 2, 3, or 5 for the reason I mentioned earlier. Then the MMP holds on 3-dimensional Q factorial KLT X, which are projective over T. And to be more precise, let me just also assume that the characteristic 0 fiber is non-empty. because in pure positive characteristic, there are certain limitations that we need to impose when working with imperfect fields. More precisely, if canonical divisor is pseudo-effective, then we make, in fact, every sequence of flips terminates, and you get a minimal model. And if it's not pseudo-effective, then you can run an MMP with scaling, which terminates with a Mori fiber space. And in fact, the result also holds in the logarithmic setting. So now let me make a few remarks. So if the dimension is 3 and p is greater than 5, this was developed in a series of papers. Maybe I should mention the work of Heikel and Shu. Kind of started and gave the existence of flips, the standard coefficients, and the work of Kashini, Tanaka, and Shu on Mori fiber spaces, among other things. The work of Birka for flips in general, and many other things. The work of Birka, Waldron on Kohn theorem termination and existence of Mori fiber spaces, among many other things. The work of Waldron, Das on the imperfect field case, and maybe also mention work of Heiken and myself on characteristic p equals to 5, and maybe many other papers. Now, the statement I wrote until recently was not even known in characteristic 0, for the reason that we had vanishing theorems only for things which are finite type over a field, which even if you assume that these of characteristic 0, that won't necessarily be the case here. However, due to recent work of Takumi Murayama, we know these vanishings in characteristic 0. So that's what happens in characteristic 0. As for the existence of flips, we use plus regularity in the work of and the strategy of Heiken and Shu. And for contractions, we use the following results. So in fact, this is also needed in the work of Takamatsu Yoshikawa. And the following means characteristic Hill's theorem of myself. So if X over S is proper, S is excellent, L is an F line bundle, then L is semi-ample if and only if its restriction to the exceptional locus and its restriction to characteristic 0 are both semi-ample. And here the exceptional locus is the union of integral subvarieties such that L restricted to V is not V. And also in our case, to show the base point tree theorem, we also used the recent result in the non-prefactorial MMP by Janusz Kolar. Okay, so let me finish by stating one application of this MMP. So when we have the MMP, we can use it to show that there is inversion of a junction for log canonical singularities. In particular, it was shown by Patakfalvi that if we had such an inversion of a junction, then the moduli space of stable surfaces exists. So we get the following result. So this holds over Z over 1 over 30, and 30 because it's 2 times 3 times 5. So you can take the moduli stack M2V bar of stable surfaces S with volume equal to V. So when Ks square equals to V, and the stable surfaces are generalizations of stable curves. So we have nodal singularities, which in this case it's semi-log canonical. It's the generalization of nodal. And the fact that the genus is greater or equal than 2, that corresponds to Ks being ample, so being amply polarized. And then we get that the stack exists as an Artin stack of finite type with finite diagonal and its coarse moduli space by Kilmori is a separated algebraic space. It's natural to answer if it's also projective. So that's what's shown by Patakfalvi, assuming the existence of semi-stable models, which is conjectured to be always true. In our setting, we can show that if the volume is big enough, and this depends on a very explicit function, which depends only on the characteristic, then the smoothable stable surfaces comprise a projective moduli space. So kind of the ones that deform to smooth stable surfaces. Okay. And now let me finish by saying that we really hope there will be many, many more applications of the theory. So in fact, there is a couple of papers that are coming hopefully soon with many more applications. And that's, I think, all I wanted to say. So thanks a lot for listening to my talk.
All right, thank you so much. So let's thank the speaker. Any questions for Jakub?
So define this plus regular, but in positive characteristic, there's also this like F split and F regular. So is there like a splitting version in mixed characteristic?
Right. So we know that F regularity implies plus regularity, but we do not know the implication in the other direction in general. If you are not Q factorial, I think it's the work of Sig, right? That if you are Q factorial, then these are equivalent. Yeah.
So my question is about like, is there some analog of log canonical?
Oh, sorry. Okay, so that's a very good question. That's another one of these things that we've been talking about a lot. So at this point, there is no such an analog. So we have some candidates for a definition, but at this point we can't prove too much about it. So somehow you see in positive, this F split, there's no Frobenius really. And so in positive characteristic, this F splitting is defined in terms of the perfection. And there's no like, it's not as easy kind of in mixed characteristic. While this R plus, which corresponds more to the F regularity, is kind of defined both in positive and mixed characteristic.
Mm-hmm. Okay, I see. Yeah, thanks.
Any other questions? So if not, maybe let's thank Jakub again. And I assume that now it's time for a social hour, right?
That's right. And I promise, let me give you the right link this time because I had to,
okay. All right.
Let's see if I can grab this one. Well, let's actually, 1 second. Should have had this ready to go. I believe this one should work. I hope. Maybe someone can try clicking that. Whoops, I sent it to, okay, I sent it privately to someone. Oh, no, that one's expired. Okay, never mind, let me try a different one. It seems like GatherTown resets its invite links periodically. So let me try posting another one. I have to log into GatherTown to grab the copy invite link. Okay, this is a new, whoops, there shouldn't be that one right there without the quote at the end. Great. That one should work. Yeah, and I'm sorry, I just didn't realize GatherTown